This is our last day of lessons.
Good morning, Professor.
And in this day, we are going to review at the beginning some of how the power plants are made to produce electricity from geothermal energy available. And then we are going to review some of the papers and some of the new technologies that are on the market now. Let's start to share the screen. And look at this brief presentation. Please tell me when you see it correctly.
Yes, we can see.
Yes. Yes.
Yes.
So this is the very simple first kind of power plants that were built in Italy, and they're not used anymore, but just to have an idea of how they were. So you have on the left-hand side your production well, and from the production well usually comes out steam and water. In a very good geothermal fields like Larderello in Italy or the geysers in California, you get just about only steam. In most cases, though, you get water and steam. Once you are at the surface, you have a separator that separates the water that goes to an injection well back. The hot water goes back into the geothermal system, and the steam is brought to the turbine, which usually is located very close to the well. You don't want to lose thermal energy and also pressure to go to the turbine, because you are going to use only the back pressure to run the turbine. So this is the turbine, and the alternator is represented by this rectangle on the right-hand side. Everything that comes out of the turbine, it goes straight to the atmosphere. So there is no condensation of the steam. Actually, you don't want the steam to condense, because otherwise the droplets of water will spoil the turbine. So you run only on the pressure that comes out of the well and is maintained and enters the turbine. Usually these turbines run at about, well, they used to run at about 5 bars. 5 bars was the pressure entering the turbine, and then you had atmospheric pressure exhaust. Efficiency was very little, because most of the energy is actually in the vapor phase as enthalpy. And therefore, very soon they evolved to this other form of geothermal power plants. This is a flash power plant with condensation. So again, out of the well or out of many wells, you have a separator, and the water goes through injection and the steam is brought to the turbine. Now, at the back of the turbine, you have a condenser, which is the one you see here. So the vapor through the turbine is condensed right on the back of the turbine, creating a depression that goes well below atmospheric pressure. And by doing this, you're actually recovering the enthalpy of vaporization that is the part of energy is the largest energy content. Now the condenser is usually simply made with the water that is condensed by the same water that is condensed by the vapor that comes out of the well and is shown this way. This is the track of the water, and you send this water into a cooling tower. The water that comes out of the condenser is about at 98 degrees, and you spray the water at the top of the cooling tower so that all the spray go down. Now at the top of the cooling tower there is usually a ventilator that pumps air out. The air enters at the bottom of the cooling tower and in countercurrent cool down the fluid by evaporation. So the fluid that is sprayed down the cooling tower evaporates in the flow of air that is then thrown out to the atmosphere. Of course, if it is very cold, the air is very cold, and so the cooling is very efficient, and a lot of the water actually condenses at the bottom here and is, as you see through this line, the water exits the cooling tower at about 25 degrees, but in winter it can be also much lower, like 16 or 15 degrees centigrade, and then it's sprayed down into the condenser, mixing up with the vapor and condensing the vapor. The condense again is recirculated through the cooling tower. Now the extra water is not shown here. It goes back into the reinjection well. So this is how most of the power plants that work today are actually working. What are the drawbacks of this kind of cycle? First of all, you would like to have from the production well as much steam as possible. So you actually like to produce steam down in your geothermal reservoir. And to do this, you simply decrease the pressure in the geothermal reservoir so that the pressure is below the boiling point of the water for that temperature. Usually, for the deep geothermal system, you have original hydrostatic pressure of about 300 bars and about 300 centigrades temperature. You reduce the pressure to about 20-50 bars, and so you start to boil off the geothermal system. And this is relatively good and efficient simply because by boiling off and producing vapor directly into your geothermal system, then you don't, you drop down all the solids, you leave a solid residue directly in your geothermal system, and these solids do not clog up the wells. If you would produce the flash inside the well, then all the residue will clog up the well immediately. And this is why you would like to produce the flash right into the geothermal system. So out of the production well comes out vapor, which usually is at the top at about 20 bars. 20 bars vapor that goes through the vapor duct to the separator at the entrance in the geothermal power plant. And this vapor goes through the alternator, through the turbo alternator, and condense right at the end here. So the first thing is that you have to reduce the pressure in the geothermal system so that you can produce the flash deep into your reservoir. Now, by doing this, by reducing so much the pressure into your reservoir, you are collecting water from wherever it can come and also from the surface water aquifer. So you tend to get into this problem of reducing the water table at the surface. Another way to do it is to start producing the flash within the well. To avoid deposition and scaling, so usually it's calcium carbonate, the main crystal that forms. To avoid producing solids that will clog up the well, you need to add to the system usually acids or inhibitors of precipitation. So you bring to the surface water with many bubbles in. You need water with some bubbles in so you can drive the fluid all the way to the pressure to the surface, because water with bubbles is less dense than simple water. So while at the surface, in the separator, you flash this water plus bubble into steam plus a water phase that you send to reinjection, or you send to a binary power plant, and we'll talk about this later. So using the flash in the well and outside the well is definitely better, because you don't need to reduce the pressure so much into your geothermal system. However, please tell me if you understand the problem of pressure within the geothermal system. So flash in the geothermal system and flash instead, beginning of flash in the well, and then completing the flash in the separator outside the well. This is very important that you understand. Can anybody say yes or no?
Yeah, we understand.
Is it clear? You have two possibilities. In the old days, they always did the flash right into the geothermal system, but because of too much pressure reduction and drainages of the aquifer, of the surface aquifer, then they started using this kind of technology of having the flash in the well and at the surface in the separator. And this is slightly better because you don't reduce the pressure in the geothermal system so much. However, in the end, you end up needing more than one well to bring your your water to the surface and flash it to vapor, because water is more dense and more viscous than vapor, and therefore you're not going to drain so much water from the geothermal system as you were able to do with the vapor. So what is the second problem that you have? Second problem that you have is that in your cooling tower, most of the heat, most of the cooling is done by evaporation of the geothermal fluid into the air that comes out to the cooling tower. And in the summer, at Italian latitudes, summers are relatively warm and hot. So during the day, you can lose 75–80% of your geothermal fluid by evaporation into the atmosphere. So your emissions from the geothermal power plant are going to be very much, and very little is reinjected back into the geothermal system. In winter, when the air is colder, then is not so much, and perhaps is lost to the atmosphere only half of the fluid. Now, these cooling towers, though, are very efficient. And by being very efficient means that you can produce much more electricity, because you need to run the ventilator, so like 2% of your electric energy goes to run the system. So you're losing some of the electric energy production to run the cooling towers. Another fact that is very bad is that since your geothermal fluids, a large amount of geothermal fluid are evaporated into the atmosphere, back into the atmosphere. This means that your emissions are a lot. And it's not only water vapor what it comes out, but also a large number of gases like CO2, for instance. CO2 is a gas that cannot condense. So what is usually done in the condenser out here, you have a pump that is called an extractor, and is represented here, but actually you have an extractor that is just for gas. So on top of the condenser, you're extracting the gases to be able to maintain a very low pressure in the condenser. These gases are mainly CO2, but these non-condensable gases are mainly CO2, but also there is a large amount, or a relatively large amount, of methane, H2S, and other trace gases like arsenic, like antimony, and usually, particularly on Amiata, a lot of mercury. There is also other elements that are in the condensed part of the water. So the water is very rich in sulfates, it's very rich in ammonia, simply because the geothermal gases are not, the geothermal fluid and the geothermal vapor are not just clean water. There is a lot of other elements that come in. Just to make, to let you understand how important this is, for instance, at Amiata, the emission to the atmosphere of CO2 is 1.5 times that of a gas-fired combined cycle for the same production of electricity. So actually at Amiata, you emit to the atmosphere more CO2 than a combined, a gas-fired combined cycle power plant. So it's not very nice from the environmental point of view. If you want to reduce the emission of CO2 to the atmosphere, well, the power plants at Amiata are not the right way to do it. In addition to the non-condensable gases, most of which we said are CO2, but also a large amount of H2S, a relatively large amount of ammonia. Keep in mind, for instance, then the power plant of Amiata emit about 1/2 of the ammonia emitted in Tuscany from all sources, including agriculture and industrial sources. So they emit a very large amount of ammonia, and the ammonia, as you know, produces by reaction with the ultraviolet light in the atmosphere, particulate matter, fine particles, and these are in the long term, even far away from the power plants, they are very dangerous for health. In addition to this, the droplets that drop down into the cooling tower, if they evaporate completely, they produce or they leave back a solid residue which is emitted directly to the atmosphere. So to the atmosphere, you have also direct emission of fine particles, and this is really dangerous for the people that live close by, because these fine particles have very large amounts of heavy metals, not only mercury, but also radioactive metals like uranium, thorium, cesium, and so on. So even though this kind of power plant are very efficient, they are not very environmentally friendly, because not only they reduce the pressure of the geothermal system and of the draining the aquifer from the surface, because very little is reinjected, but they emit to the atmosphere a very large amount of pollutants and greenhouse gases. Let's go. Is there any question? Please answer yes or no.
Yeah, just one thing that I have not understand. If it is, it creates a very large amount of pollution, or if not create a great amount of pollution?
It does create a relatively large amount of pollution. But the pollution depends really on how polluted are the fluids that you are exploiting. In some of the geothermal system is really mainly vapor what it comes out. This is usually closer to the tropics, where you have a lot of rainfall and very good geothermal water, and particularly if you're far away from magmatic systems. Magmas usually have a very large amount of heavy metals that go with fluids, and therefore your fluids are not very good. So really it depends on the kind of fluids you have. Now in Tuscany, the fluids have a very large amount of non-condensable gases, so this is about the only technology that you can use at the moment. Because the non-condensable gases, you have to throw them directly to the atmosphere, otherwise they clog up your system, and you're not going to be able to produce electricity anymore, because the pressure in the condenser is not low enough. So it really depends on the kind of fluids. Now at Amiata, where these geothermal fluids have created probably among the largest mercury mines in the world, and of course these fluids are full of mercury and full of other of H2S, full of CO2, and full of any possible, so the pollution is very high. Even CO2 is very high, and the CO2 usually comes because of reaction and decarbonation reaction of the limestones that are contained in the geothermal system. But for instance, if you have geothermal system in granitic rocks, then they will have much less CO2, much less non-condensable gases. Did I answer your question?
Yeah, thank you.
Professor?
Yes.
What if we use a double stage or two-stage steam turbine? So we can increase the efficiency, electricity?
Yes. I'm not going to show you this, but you can also have a two-stage, and since the water that comes in the separator as it enters the power plant is at very high pressure, usually 20 bar, then you can have a second stage of vaporization at low pressure, say at 5 bars, and then this vapor, you run it again through a second turbine. So you can have a second turbine to produce more energy by the hot water that is at high pressure in the first separator, say at 20 bar, and then you drop the pressure to 5 bars so that the water can vaporize again, and you're running this vapor through the turbine, condensing again at the end. So usually you have two turbines, two condenser, another separator, and you use the same cooling tower though.
Yes.
But even if it is more efficient, the environmental problems are the same. Now in Italy, they use now what they call AMIS, which is abatement of hydrogen sulfide and mercury. And so the way they do it, they oxidize the H2S to SO2, and then they dissolve the SO2 into the geothermal fluid. And by doing this, in emission, you don't have much H2S. However, by dissolving the SO2 into the geothermal fluid, you displace the calcium carbonate and you form calcium sulfate, and you produce more CO2. So into the emissions. In addition, what they do, they can add also ammonia to, if there is too much SO2, then they add ammonia into it. Or if there is too much ammonia into the geothermal fluid, they add sulfuric acid to produce ammonium sulfate, which is very soluble, and then can remain in solution into your condensed water. However, since the droplets that come down from the cooling tower, they evaporate, you tend to produce more fine particles in the emissions. Now, keep in mind that up to a distance of about 400 meters from this kind of cooling towers, there is what is called the lichen desert. So lichens cannot grow because pollution is too high. So there is a very large amount of pollution around cooling towers. Trees like oaks they usually die. They only can survive trees that can stand acidity in the air and on the ground. Usually pine trees and these kind of trees. So, but if you have very large amount of non-condensable gases, this is about the best you can do. Oh, sorry. Let's see the binary cycle. Now, for two reasons. First reason, to try to avoid emission. Second reason, to try not to decrease too much the pressure within the geothermal system. And also, if you don't have very high temperature in your geothermal system. So if your geothermal system, you have temperature around 180 degrees or slightly lower than that, then what you would like to use, particularly if your geothermal fluids are not very good, is a binary cycle. How does it work? It's very simple. From your production well, your water plus bubbles usually go into a first heat exchanger, and you exchange your heat from your hot water, hot geothermal fluid that come in to a secondary fluid, usually is a low boiling temperature fluid, usually hydrocarbon, and then the vapor of this secondary fluid, you run it through the turbine to produce electricity. Then you recover your fluid at the end past the turbine, and you pass it in a second heat exchanger, which is the condenser, that runs. There are two types of condensers, on water or simply on air. What is the good thing about the cycle is that no geothermal fluids is lost to the atmosphere. So you have no CO2 emission, you have no pollutants emission, you don't have fine particles emission. Of course, in this process, you lose efficiency. And I'm going to tell you a few numbers. Now, to run I think we discussed this the day before yesterday, a 20 megawatts geothermal power plant flash uses 130 tons of geothermal water per hour. To produce only 6 megawatts of geothermal energy in a binary cycle, you need about 600 tons of geothermal water. So you practically you have to produce, just to make a rule of thumb, to produce 4 times less electricity, you need to circulate 4 times more geothermal water. Why is this? Because you are not using the enthalpy, you're not bringing out the vapor. Most of the heat is actually contained in the vapor phase. Now, if you're bringing up water, even if it has a slight amount of vapor, but really you are using the water and you are decreasing the temperature of the water. So the more or less is 16 times less efficient, the binary cycle relative to the flash cycle. And this is why in most cases, particularly in underdeveloped countries, where they don't care much about pollution, everybody tends to use flash cycles because they're much more efficient. They can produce more electricity. Now, whenever you are concerned instead about environmental problems, you like to use binary cycle. What is the drawback of a binary cycle? That if your gases, if your non-condensable gases are very high in percent, and this is the case of Italy, then it's very hard, as you bring the water up the well, because of the decrease in pressure, because within the well you have sort of a hydrostatic pressure column, then as you bring the water up, then the water will start to boil, and your non-condensable gases will go all immediately into the vapor phase. But then when you, after you pass your fluid into your first heat exchanger, then you have a two-phase fluid, a fluid that is made of non-condensable gases saturated with water and a liquid phase that is saturated in non-condensable gases. Now, you need very high pressure to be able to push these non-condensable gases back into the water, into the liquid phase. And even if you do that, and if you attempt to do that at depth, these non-condensable gases try to exsolve as soon as they can and come back up to the surface through the impermeable cover. Now, the impermeable cover is never really totally impermeable, and in time will allow the gases to come to the surface. Or, since the gases are much more mobile than the water, the gases will flow directly to your production well, and you will produce a short circuit, and you will start producing cold, non-condensable gases very soon. So you have to be very careful that you don't want to have a lot of non-condensable gases in your fluid to use a binary cycle. Now again, if you're in the cooling tower, if you are able to, you're in the tropics, you have a lot of water, you might have a river, so you can use a very efficient cooling tower, run on water, evaporating water. But you need to use fresh water, probably usually from a river or from a lake. And this water is going to be evaporated in the atmosphere, so you're going to lose the water. And this means I can use this only wherever you have a lot of water at low cost. Otherwise, you will have a cooling tower that is run just on air. And you will have a ventilator that pumps the air, and the heat exchanger, this heat exchanger here is actually right into the cooling tower. And this is much less efficient, and you're losing a lot of energy by running all the ventilators, but that is what you can do. And most power plants, particularly in desert areas, like in Nevada, for instance, or in California, binary plants are all only run on air. Now, since the cooling towers are much less efficient if they're run on air, that means that you will need a much larger space on the surface where you need to put your cooling tower. So your cooling tower is about 10 times, occupies about 10 times the space of a cooling tower run with water, with evaporating water, an evaporating cooling tower. Any question? No questions?
Not at the moment.
So one other drawback of the binary cycle is that since you're pumping out a lot of geothermal water and you're reinjecting a lot of geothermal water, then you're going to produce seismicity, induced seismicity. Now, in many cases, this is not a big deal. In other cases, particularly where you have old villages made of poor masonry, no concrete, this can be a big problem. And this has been a big problem in many of the geothermal fields in Germany, in Switzerland. Not all of them, of course, but if you have conditions of active tectonism with recurrent earthquakes, then you have to be very careful not to produce seismicity because people will make you close the power plant immediately. So let's make a resume of the comparison between flash power plants and binary cycles. Flash power plants are more efficient. They are very good whenever your geothermal fluid is mainly made by water, and even if you have large amount of non-condensable gases, they can run relatively well. Although they reduce the pressure significantly, the pressure of the geothermal system, and you have a lot of emissions to the atmosphere. So only if you have very good geothermal water, mainly water, then you can safely use these power plants. Otherwise, you produce a lot of emissions that are both gaseous emissions and solids or fine particles emission. Now, if your fluids are not very clean, then you better use right away binary cycle plant where you have no emissions. But you can do this only if your condensable, non-condensable gases are low in content. Otherwise, you won't be able to use it. The other drawback is that you're going to use and to circulate a much larger amount of geothermal water, about 15–20% more for the same amount of electricity produced than a flash cycle. And because of this, you are probably able to induce a much larger number of earthquakes. Any question?
No.
Okay. And this is some sceneries taken from Italy just to show how important, how is the impact on the environment, also from the landscape point of view. Now, the one on top left is the power plant that is present on Mount Amiata. Mount Amiata is here on the back, and you can see that they have done a relatively good job in trying to mitigate the impact of the power plant by giving a green color to the power plant. Now, if we go to the other sections, these are the older power plants at Larderello, and these are, while the one on the top is a cooling tower with ventilators on top, the one on the bottom and the other three are cooling towers which natural draft. And this cooling tower can be very high, while the cooling tower on the top left is about 15 meters high. This other cooling tower can go up to 100 meters. So, however, the emissions in the atmosphere are smaller because they are so high and there is not a draft of air that is forced by the ventilator. In the old days, the cooling towers were all with natural draft. And you can see that the one on the top right is one of the old, is an old picture of, and in the old days, they used to have emissions just about everywhere. Whenever they didn't want the fluid, and they emitted to the atmosphere. So they had a really bad environmental impact. Today's everything is, they try to contain everything, and so it's much less pollutant than in the old days. But still, you can see, say on the lower right, you see these old houses, old farmhouses, many of them still people live in, with these huge cement high towers that really spoil the landscape. Now, I make a comment, and I would like you not to be offended. Now, what engineers usually think about beauty, they think everything that works is beautiful. But that is not actually the case. So it's very important that engineers collaborate with architects, usually, or landscape architects, to try to mitigate the impact of their power plants because they can be pretty bad. Now let me show you what is the next generation of power plants, which are coming out. They started to build them last year, but this year there are already many projects beginning to be working. Beginning to be working. They are beginning to develop. The idea is very simple and is to try to have a heat exchanger directly into your geothermal system. So you are not bringing fluid to the surface, because bringing fluid to the surface means to bring very nasty fluid to the surface. It also means you need to reinject this fluid down to the ground, producing seismicity. In this case, what they want to do is to just extract the heat from the rock formation. Let's see if we can. Okay. So can you see the small picture here?
Yes.
Yes.
And actually it's pretty interesting because what they do, they drill a well, say to about 2 to 5 kilometer depth, and from another location about 5 kilometers away, 2 to 5 kilometers away, they drill another well. And then using shale gas technology, they are able to construct a number of horizontal wells, and they are able to meet this well somewhere in between the two wells. So they actually are able to produce sort of a radiator, a heat exchanger at depth. Now, the idea, what they want to do is to have two power plants, and so they will extract hot water from one side at depth, circulate the water and extract the heat and produce electricity, reinject the cold water, warm it up at depth, and reuse it in the second power plant to produce electricity and reinject it back. So this is done by a company called Ivor in Canada, and I think it's very efficient, very efficient. I'll tell you about the efficiency. It's very efficient if you consider that the impact, the environmental impact is very little. Now, the only environmental impact you have is during construction, but consider that to create a binary power plant that would produce something between 6 and 10 megawatts electric, you need 4 years, 3 to 4 years, to produce something like this, you do it in about 6 months. So it's very fast. And in the pipes, the horizontal pipes that you create at depth, you practically have, they're totally isolated from the formation, so you're draining only the heat out of the formation by conduction. Now, if you remember yesterday, we were looking at scaling the equations, and we said that conduction at the very most is going to be important over 100-meter distance. Now, the pipes below here they are about 100 meters away, one from the other, so that each pipe can in time drain the heat from about 50 meters away from the pipe itself. So conduction can still be important. In addition to this, you have practically a very large surface, because you can have you can go to the side about 1 kilometer, setting about 10 pipes, 10 horizontal pipes, 5 kilometers long and 1 kilometer wide. So you're really trying to drain the heat from a very, very large surface area. Well, here is the closed loop. I can share with you this presentation if you like, and I will send by email to you later on.
Yes.
Yes, would be nice.
Okay, just to show you, this is a shale gas field. And you can see how they're able to drill horizontal pipe. They go down in this first part by 5 kilometers, and then they drill horizontally one after the other in a very efficient way. And in rocks that you don't care if they're permeable or not, because you're going to use only conduction. So you can drill also in clays. And you don't need to have very high permeability. Actually, you don't want to have high permeability, so that you're sure that you're not interacting with your geothermal aquifers.
I've got a question.
Yes, please.
I didn't understand if each pipe can gather the heat from 50 or 15 meters away.
50.
50?
Yeah,
Wow.
50. Now, most of the heat will come from the first 10, 20, 25 meters. Right? There is where you're going to really to drain the heat very efficiently, but in the long term, then you can go, the heat will be drawn about 50 meters away for each, as a radius, right, around each of these pipes. So in the end, you are going to drain your heat, say, 5 kilometers, sorry, 5,000 meters times 2 kilometers times 100 meters. So, from a relatively large volume of rock, which is sufficient for you to run the system for about 10, 20 years. And since, because of shale gas, the cost of drilling has dropped down tremendously with the shale gas technology, then you're able to build this system in a very efficient way. Just to make a comparison, now a 5 megawatts geothermal power plant made with a binary technology, you need to build something like 17 wells, say 15 in the end. 15 wells at a cost, say about 2 kilometers deep, and at a cost of €1 million per kilometer. So each well will cost by itself about 2-3 million euros. So it will be 20, about 30, 40 million euros is only the cost of the wells, plus the cost of the power plant. So you end up something between 60 to 80 million euros. That is going to be the cost of a binary power plant that produces 5 megawatts electric. Now, to produce 5 megawatts electric with this system using shale gas technology, it costs about the same. So you don't achieve the efficiency of a flash power plant. You're still perhaps 5 times less than that. However, your environmental impact is almost dropped to zero. The only thing you can expect is to have a little bit of earthquakes, because by cooling the rocks, you're contracting the rocks. But these earthquakes are going to be very superficial, perhaps at most 5 kilometer depth, and localized in the area. So the energy that can have this earthquake is never going to be very big. Again, if you would use this to produce just heat and use it as heat directly, then this is even more efficient, no? Now, this graph here, it tells you how in time, you see, it tells you the depth of the holes and the days you need to drill that well. So a 9 kilometer deep well with shale gas technology, you can drill it, say, in about 9-10 days, which means only you go a kilometer a day. It's a technology that is totally different. It runs on very high pressure mud and is so efficient, then you can be so fast. And the cost of a well is really how long your drilling equipment is going to be on place. Now, to do a normal geothermal well usually can take up to 6 months. So you are comparing a cost of the drilling rig 10 days against 6 months. So there is no comparison. Okay, well, this is what I wanted to show you. There is also a new technology that can, in theory, can be applied to this as well, to this kind of technology, and is the instead of using a turbine to produce electricity, you can use the thermoelectric effect. So you practically have a cell which is about 0.5 centimeter thick and 2.5 centimeters by 2.5 centimeters in a horizontal dimension. So a very thin wafer of a material that has thermoelectric effect. And that means that if you put a high temperature gradient across that cell, then you produce electricity in the direction of the cell. Now, you can put these small cells in series, and so you can actually have hot water on one side and cold water on the other side, and you are able to produce electricity, which is very efficient. These days, they can create these thermal cells with this thermoelectric effect that reach about 10% efficiency at a relatively low cost. At the moment, they're running this equipment on the surface because these cells can break down, so on the surface it's much easier to exchange them. But the ideal would be to put these cells right down into your pipes, into your geothermal system, even this kind of geothermal system. And therefore, instead of bringing hot water to the surface, you would like to bring cold water down to cool and keep cool the one of the surfaces of the thermal-electric cell. What is the advantage of this? Is that it's much easier to bring cold downward than to bring hot water to the surface. Why is this? Because you can simply compress a gas, cool it down, and send it down to the bottom and makes the gas expand, and then by diabatic expansion, you could right away cool down your self-surface. So the combination of this kind of Evo loop technology plus this thermal effects, thermoelectric effect is probably going to be the future of geothermal energy. Any question?
And this new kind of technology is all referred to also to the Seebeck effect theory or not?
To the thermoelectric theory?
Yeah.
Yes. Let me see if I can show you because I'm sure I have in some of my presentation, I have this effect shown. Well, let's try this presentation. I'm not sure if I have it here. Okay. So we have, this is the, well, is another kind of technology. It's not the Evo technology, which I think at the moment is the best. But in Japan, they were trying to use just a single well and running hot water down the well and up again to the center to drain the heat by conduction. But the surface area of these vertical wells is very little. So they can work only if you go to very high temperatures. This is the power plant in Japan that is trying to use this technology. This is the thermal effect, thermoelectric effect, and you can see this is a ventilator that is spinning by the electricity produced. Let me enhance it a little bit. This is a plate, a cell that has a thermoelectric effect, and there's a candle down here that is warming up the base of the cell, and then the top of the cell is cooled down in part also by the ventilator through this system that you see of pipes. So the ventilator runs actually on the heat of the candle. And this is the system that has been developed at Stanford in California, in which you have hot water and cold water running this is cold, this is hot, this is cold, this is hot, cold, and hot. So you have cold water and hot water, and in between you have your cells. And this is how they produce electricity. So this is just experimental, but they are able now to produce 100 kilowatts of electricity with this system. It's not a lot, it's not 1 megawatts, but this is where you would like to get to. Okay. Any question?
And how much difference of temperature do you need for producing electricity in this way?
The ideal is 100 degrees. So your hot point, your lower part, is 100 degrees above the other side of your cell. So the technology to make them and to make it durable in time is not is still not well developed, simply because you can imagine your thermal stresses in that cell that has to go to room temperature to 100 degrees difference between one side and the other. So thermal stresses are really what tend to break down in time these thermal cells. If you could keep it always at the same temperature once you apply your thermal stress and then never change it, then be fine. But in time, you're going to need replacement. You need to cool down your well. You need to warm again the well. So for now, it's very hard actually to put them in the well. But that would be really the last goal, right? Now there is an investor, an Indian investor, that is actually trying to use an even more expensive. This technology is not very expensive. This technology has the cost of a normal binary plant. So it's not very much. It's affordable with the thermoelectric effect. Now, what these persons in India are trying to do, they are trying to use graphene to bring the heat directly to the surface. You know that graphene, the crystal of graphene, is a super conductive material in the direction parallel to the crystal lattice. And it's practically a total thermal isolator across the crystal lattice. Graphene is made of hexagons of carbon atoms in planes. It's like graphite, but it's made in the lab. And so you could have, if you have a depth, say 300 degrees, and you are able to construct a pipe of graphene or a cable of graphene to bring this heat to the surface, it's not very easy to do it and is extremely expensive. Then you could have you need some thermal gradient in the rock, and say you can, so you drop down the temperatures in the rock from 300 to 200 degrees, so that you have a 100 degrees thermal drop in the rock, and conduction can bring your heat to a graphene cable. Then you could have your 200 degrees right at the surface. So, and that is the ultimate goal. I doubt that they will ever develop this unless in very expensive environments. Perhaps, I don't know, in other planets like Mars or the moon, where you don't have water or fluids to bring the heat to the surface. Any additional question? These are the new technologies, and I think they're very interested. I myself would love to start working on graphene as well. But if you don't want to overshoot, the thermoelectric effect is really relevant and very interesting, because it can also be applied to transfer heat in much smaller environment, and also to accumulate heat into rocks, also by running electricity. So I think it can be very, very interesting. Shall we go ahead? Any other question?
No.
Okay. So let's start and looking at some of the modeling that I have done through times. Is not that I want to do, but some of this modeling I think is very interesting for you, or at least is very interesting to know about. We have been talking in the past few days, and even today, of how important it is to avoid non-condensable gases, mainly CO2. Now, however, you remember that we discussed this, that in the old days, the first power plants that they were running directly on CO2, running the CO2 directly to the turbine at Amiata, because there were CO2 gas caps, and therefore there was so much CO2 that you could run it right straight to the turbine. So about the year 2000, people started to wondering if you could use actually CO2 instead of water to run a geothermal power plant. What are the advantages of CO2? The advantages of CO2 are various. First of all, above 32 degrees, about 32 degrees and 70 bars, CO2 is a supercritical fluid, so it's not a gas. It has the density of a liquid and the viscosity of a gas. Therefore, it's very mobile. And because of the very high density, has also a lot of heat content in the fluid. So you combine a fluid with a relatively high heat content, even if less than water, but a viscosity that is orders of magnitude less than water, because it's the viscosity of a gas. And so there have been a number of experiments to run geothermal power plants with CO2. And actually, I've been proposing to run wherever you have a high CO2 content in your geothermal system, you could try to use CO2 to run your system instead of water. Now, by doing this, you might be able also to sequester some CO2 from the atmosphere. So it can be also beneficial for the environment. Now, let's see this simulation and let's see how it works and how it goes. Now, suppose in here you see 5 wells. 4 wells are relatively deep and are the green wells. And 1 well is less deep and is the red one. Now, this is called the classic 5-well problem. You can extend this 5-well problem on a surface and repeat it to infinity. And you have 1 well where you recover your fluid, your hot fluid, and then you have 4 wells around in which you reinject the extracted fluid. And you have a power plant here at the center, and then a conduit that will take your CO2 back down into the ground. Now, the distance between the vertical distance between the producing well and the injecting well is about 1 kilometer. So these wells here inject at about 5 kilometer depth, and the production well produces at about 4 kilometer depth. These 5 kilometers, 4 kilometers, why is important is because you don't need a very high geothermal gradient to be able to reach high temperature or temperatures that are high enough to be interesting from the geothermal point of view. Please, do you have any question on this geometry? Some of you say yes or no.
No. Is it clear?
Okay, so by symmetry in this geometry, you can simulate only this triangle. And then symmetrically, this triangle is reflected in this other triangle to make a square. And then each of the square can be multiplied out into the whole area. So you actually need to simulate only this prism with a triangular face as opposed to the whole area. And again, why is this? Because with TAF2, as we discussed, you cannot go much more about a few tens of thousands of cells, because otherwise you are not able to run your problem. So we are going to model only the area that you can see here. And this is how, these are the cells that your model is composed of. Cells are on the top part 25 meters across and 25 meters in depth. So it's a relatively narrow and small cells. Now, in addition each of these cells is split up into matrix and fractures. So each of these cells, you have a matrix and a fracture. The matrix has porosity, and the permeability is only related to the porosity, while the fracture cell, the permeability is only related to the fracture. And of course, the permeability of the fracture is larger than the permeability of the matrix. You inject cold CO2 at 20 centigrade, 20 times 10 to the 5th Pascal, which is 2 megapascal above hydrostatic. So with a tiny little bit of pressure, and you extract heat from the top left, and you try to extract heat at 140 degrees centigrade with 2 megapascal pressure below hydrostatic. So hydrostatic here is 3.5 kilometers from the surface. So you are at 350 times 10 to the 5th Pascal, which is 35 megapascal. So you are extracting at 33 megapascal pressure. 35 megapascal is the ambient pressure, and you are injecting at 20 down here is a kilometer, so as opposed to 35 is going to be 45 megapascal, so 47 megapascal pressure, 4.5 kilometers. On the rocks on the surface on the surface of our model are 160 centigrade, but you extract at 140 so that you are able still to extract heat from the top. So you are at the beginning injecting CO2, supercritical CO2 down at the bottom here. This CO2 expands into the system and is recovered eventually out here. At the beginning of the model, the full model is filled with water and salt. So the CO2 creates a plume that will drive the water away until the CO2 is able to spring out of the producing well. So this is about what you see. You have the logarithm of time in the bottom axis, and you have the mass flow rate, kilogram per second on the left-hand axis, and you had the heat flow rate on the right-hand axis. And then you have a number of lines that tells you what is happening in the system, actually what is happening at the producing well. Now, at the very beginning, see the dark blue line. The dark blue line is the H2O flow rate. So from the producing well at the beginning, you are producing just hot water. Remember, hot water at 140 degrees centigrade. You see that in time, the hot water production increases a little bit. And the reason is, and explain it to you going back here, as you develop your CO2 plume, the pressure gradient, since the CO2 is so low viscosity, the pressure gradient, the pressure drop is only in the water. So as you develop your CO2 plume that goes towards the producing well, then the distance in which you have the pressure drop decreases, and therefore you produce more. And so this is your production. Now, as soon as the CO2 springs out of your producing well, there is a very strong drop in production of water. There is also a strong drop in production, there is a strong production of water. Now the CO2 is the green line. So at the beginning, you practically produce no CO2, and as soon as the CO2 start to flow into your producing well, then you increase the production of CO2. This is obvious because since the CO2, the supercritical CO2 has such a low viscosity, you preferentially drain the CO2 out of your system, and your water almost goes to zero. However, at the beginning, let me show also the red curve. At the beginning, the red curve follows the increase in heat production because it follows the increase in water production. Now, as soon as you start producing CO2, your heat production drops. You see this first drop in production of heat, which is the red line. And this is because you're going from single phase flow to two-phase flow, which means that in your well are coming in a lot of bubbles of CO2. And because you're flowing this two-phase flow through the fractures, the actual permeability, the actual average permeability of the system decreases because the droplets of water occupy space while the CO2 is trying to flow through them. And therefore, you tend to clog up the system a little bit. You are producing less fluid, and you see this, there is less water. If you see the liquid flow rate is the dark green. Gas flow rate. So you're producing less fluid and you're producing less heat. However, as soon as the amount of CO2 increases to the point then that your water is very little, then your heat production increases a lot, and actually increases well above and almost twice as much in the end the production of water. So your production is better, your heat production, the one you're concerned with to produce electricity, is better than just producing water. It's more, you are draining the heat out of the formation more efficiently with your CO2 plume than with your hot water plume only. And you still produce a lot of heat with your system as long as the water is very little. Now, if you see there is a liquid flow rate, which is the light blue, and H2O flow rate, which is a dark blue. The liquid flow rate, you see at some point it goes to 0. When the liquid flow rate, which is liquid water saturated with CO2, goes to 0, it means you don't have any more your liquid phase. However, you have, and so your to the wells arrive only a gas phase made of CO2 with saturated with water. And now, because the saturation, which is vapor, the water vapor has a lot of heat content, this is where you produce the most of your energy, because not only you have the heat on the CO2, but also you have the latent heat of vaporization into the water contained into the CO2 plume. Now, at some point, you have so much CO2 to the system that you have dried out your system, and there is no more water vapor reaching your well. And at this point, you see a total drop in your production on everything of heat and also of fluid. Does anybody can guess why you have this drop in production? Well, the reason is that as you dried out your system, you start precipitating the salt contained in the water. As long as you have a liquid phase, the salt will tend to remain in solution into the water. But if you dry out the system, then your salt will precipitate into the fractures and will clog up the fractures and will not allow the CO2 to flow through the system anymore. So this kind of model predicts that very soon, if you dry out your system, you are going to clog it out. The ideal is to actually run it with a little bit of water, not a lot of water, with a tiny little bit of water, so your salt cannot precipitate and cannot clog up the system. How you go around to unclog your system? Well, one simple way is to produce induced earthquake that will crack up the salt crystals that clog up your system to allow the gas to flow again in. And of course, this has not been modeled here, and this is because you have this big drop. Another way is to try to solve again your salt, your precipitated salt. But this is more difficult because if you say you want to flush the system with fresh water, then the water will not go where the salt is because the salt is clogging up the system. So it's not very easy how you're going to go around this, and the best way is to produce earthquakes that will fracture the rock and will fracture the salt and allow the system to be open again to fracture permeability. Now, one way we were trying to do is to re-inject a little bit of water so that we are not going to have so much salt precipitation. But if you re-inject water, then you're going to run the system in two-phase flow, And that is what you observe on the right-hand side. So your system is running most of the time in two-phase flow, and therefore is not very efficient in bringing the heat to the production well. The true permeability of the system decreases, and therefore your CO2 is not able to flow to your production well fast enough, and you're not producing enough heat, or you are producing enough heat, even more than just water, and for a longer time. But then at some point, you are still going to dry out the system because of salt precipitation. Any questions on these two figures?
No.
I have
Yes.
a question.
Yes, please.
So this kind of injection could be used also if you have let's say, oil well that is no more producing.
Oh, yes. Actually, one of the idea is to, once your oil wells are not producing anymore, and particularly gas wells, and particularly from shale gas, you have all these wells down in the ground, already laid down, and they're not productive anymore, but you are in a place where you could start to produce heat. Mm-hmm. And so some of these wells could be turned into producing geothermal energy. And since the wells are drilled already, then probably the cost of running a geothermal power plant are not so high. Mm-hmm. Now, why is it not done? Simply because the money production of an oil well or a gas well is so much more than any geothermal well that oil companies don't like to go into geothermal. They simply want to continue to exploit and go and move somewhere else where they can get oil or gas. Geothermal energy to produce electricity is not a very cheap way to produce electricity. Mm. So this is the main reason. Oh, we are an oil company. We don't want to bother with geothermal energy. However, in places where you produce oil or shale gas, and you are far away, far off your electric grid, then you can perhaps think on using your exhaust oil well or gas well to produce the electricity that you need, for instance, to pump the oil out of your wells. So there are cases in which now oil companies tend to like or start liking to produce the electricity through geothermal energy. One of this is Shell. The Ever project that I've shown you is also financed by Shell. Because of course they have so many wells that have been drilled for shale gas, and shale gas well, each well for shale gas can last 1.5 years, 2 years, that's it. So they produce a lot of money in little time, but then that well remains there and no one knows what to do with it. Did I answer your question?
Yes, thank you.
Any other question? So let's go. And see what is actually happening on the reservoir. And on the left-hand side, you have your system after a few months, after 1 year, after 5 years. On the right-hand side, you have the same systems, but you're injecting brine plus CO2. And you have only CO2 injection on the left-hand side. This is what is happening in the fractures. So you inject on the lower right corner and you produce on the upper left corner. The colors within the model are the concentration, the volume concentration of salt into the fracture. So what you see is that as you start injecting, your CO2 plume develops into your aquifer, then you have a front of salt precipitation, which is about 10–15%. So salts start to precipitate in the fractures, and as time goes by, this salt precipitation front moves towards the production well. And after 5 years, you can see, has reached your production well and has clogged up your production well. So in this case, you should pump fresh water at high pressure into your well to try to produce fracking, to try to open up your system again so that you can start again your production with CO2. Now, if you inject brine plus CO2, as you remember the graphs before, you produce less heat, but after 5 years, you have not reached yet your production well. It's only at around 10 years that you're clogging up your system. Now, why, if you have brine injection, you sort of have two fronts which move forward. And the reason is one front is where your CO2 plume is, and the second front is where your CO2 plumes tend to become two-phase flow with your brine behind. So you sort of have these two fronts of salt precipitation that move through your system. What is at the end? At the end, then perhaps you last longer, you last 5 years by injecting your brine, but you are clogging up your system more if you inject brine and CO2. So you have a sort of a drawback. You can produce for a longer time. However, you are clogging up your system more. Okay, now here you have the solid saturation. Solid saturation means how much salt is actually clogging up your fractures. And again, on the left-hand side is if you inject CO2. On the right-hand side is if you inject CO2 plus brine. So at the beginning, you have a little bit of clogging in the production well. And then at the end, though, your clogging is only at the producing well after 25 years. Now, if you inject brine instead, you also have some clogging close to your injection well. Okay, so this is a simple way, but I think it's very interesting because in many cases, particularly where you have high non-condensable gases already present, and perhaps you have also gas traps like they were present at Amiata, and these gas traps were mainly made of CO2, like 90% CO2, then you can think on running your system directly on CO2 without using your water. And this will allow you not to drain the water out of your superficial aquifers, as it was done. At that time, they had no idea that they could use CO2 directly. They not even thought about that. But today, perhaps it could be if you shut down your plants at Amiata, perhaps you could start using them again in a few years just by running through your system at a much lower temperature, so by using a binary plant. The only problem of using this is that the CO2 gas is so rich, even if just in traces, is rich of mercury. And therefore you expect all your iron and steel piping to be contaminated with mercury as an amalgama at the end of your production. This means that at the end of your production, you have a steel that is very highly contaminated with mercury. And so if you dismantle your system, you're going to produce a lot of toxic waste material. So you have to be careful when you do these things, and you have to think about, in the end, what would be the environmental cost of your system.